And we're live.
So lesson 1, introduction to vectors. Patrick the puppy goes wandering around his neighborhood, as seen below. Notice a series of arrows drawn on the map of a physics teacher's front lawn. Each arrow shows the magnitude, the size, and the direction of a series of successive trips made by Patrick the puppy. These arrows, showing both magnitude and direction, are called vectors because they show displacements. Okay. When Patrick reaches his final spot near the car door, how far has he walked since he left his porch? Well, Manny, it depends what you mean by how far. If I simply ask how far in terms of distance, well, Manny, my friend, how far from here to here? Look at the picture and figure it out. How far from here to here? 5. How far from here to here? Oh, okay, there. How far from here to here? How far from here to here? Okay, so you know what? We could say his total distance was, if we really break it down, 3 plus 2 plus 4 plus 4 plus 2 plus 4. This is also good review from the very beginning of the year. The distance would be 3 plus 4 is 5 plus 4, 9, 13, 15, 19? Double check me. It's going to be 12 plus 7. 19? Yeah. Displacement. Well, I think the displacement is that right there. How long is it? Well, how long is that right there? 3. How long is that right there? 4. Hey, I can use Pythagoras to figure out how long that is. I can go a squared plus b squared equals c squared square root. Could you on your calculators or in your heads go a squared plus b squared equals c squared square root? How long is this vector here? What's its magnitude? And then it said there was a 53-degree angle there. Let's put a compass here. North, east, south, west. And here's how we can write his displacement. All vectors have magnitude and direction. What's the magnitude of his displacement? What was it? What was the magnitude of his displacement? What was it? 5. And then to show that we're about to give the direction, we put an @ symbol. And then we would describe this direction by saying 53 degrees east of north. 53 degrees east of north. Say what? East of what? East of what? Again, east of what? Here's what that means. Go north and then go 53 degrees east of north. Okay? This is how we're going to be doing our direction notation. And people have trouble with this. If you feel a little confused, don't freak out. I'll spend lots of time. But it's always east of what? The of what is what you draw first. And then what was said first is the direction you tilt from there to get the angle. Note, there are 2 ways to indicate that a vector quantity is a vector quantity. In diagrams or in handwritten notes, a small arrow can be written above it, although we've gotten lazy, Jake, over the years, and it's become a half arrow. In other words, distance, displacement, distance, displacement, distance, displacement. In typing in a physics textbook, which I'm not a big fan of, it's always done in bold font. And the reason I'm not a fan of it, Emma, is for me to use bold font would be like Well, that's stupid. That just takes so long, too long. So I like the vector notation. Okay? If only the magnitude is importance, the symbol D, plain italics, is used. Or sometimes I won't use that, but I'm showing it to you. Hey, those of you in pre-calc, you've seen that symbol before. What do those two vertical lines mean when they're around a number? Absolute value. All absolute value cares about is how big the number is, not its sign. In physics, how big the number is, not its direction. So that's the shorthand notation. So, scalars and vectors. If you add 3 kilograms of sugar to 2 kilograms of sugar, you'll have 5 kilograms of sugar. If you add 3 liters of water to 2 liters of water, you'll have 5 liters of water. Masses and volumes add together like normal arithmetic. They're scalar quantities. Scalar quantities have magnitude but no direction. Hey, what are some scalar quantities? You've learned some finally this year. What are scalars? Give me some examples. Oh, joules is a unit. What does it measure? Okay, energy is a scalar. In fact, I'll go energy / work. Time. Power, because power is work over time, scalar over scalar. Speed as opposed to velocity. So 3 meters plus 2 meters is 5 meters. 3 meters plus 2 meters can be 1 meter. 3 meters plus 2 meters can be Pythagoras, depending on the direction. So if you add a 3-meter displacement to a 2-meter displacement, it can add to 5, same direction. It can add to 1, opposite direction. And you can get any value you want to in between, depending on how you set up that second vector. I've showed you a few ways it can add up. So what you see is in figure 5.3, in this one, you're seeing how we add vectors according to the rules of vector addition. We're going to spend a lot of time talking about that. The resulting displacement depends on the directions of the vectors. Hey, what are some other vector qualities? So displacement is a vector. What else? Velocity. What else? Momentum. I'll say impulse / momentum. What else? Force absolutely is. And the reason force is because what? Because force is ma. Mass is a scalar, but a is not. So acceleration. Let's suppose you're adding 2 force vectors, 7 newtons and 4 newtons. What's the maximum force you could create from a 7 newton force and a 4 newton force? 11 newtons. That would be 4 plus 7. What's the minimum force you can create? Yeah. 3. You could argue -3, but I'm not. 3. In terms of magnitude, 3 newtons. And then if you add them together at angles, you can get every value in between there. Turn the page. Vector addition in 1D, 1 dimension. 5 meters east plus 3 meters east. This one we could do already in grade 10. 5 meters east plus 3 meters east is what? By the way, if it's directly north, south, east, or west, we don't put an at symbol there. We just go east. It's when there's an an angle, then we use the at symbol. 6.2 newtons to the left added to 6.7 newtons to the right. In fact, what we're really doing is kind of a winner minus loser routine. In the first one, hey, they were both winners. We went winner plus winner. Here, we would say, who's winning? Right is winning, so it's going to be 6.7. Take away 6.2. Answer? 0.5 newtons to the right. No big surprise there, Jeff. By the way, that third vector, the answer, represents the sum of the first two vectors. It has a fancy name. It's called the resultant. The resultant. Result with an ant on the end of it. Now, Rob, the moment you've been wondering about. Let's add them in 2 dimensions. What if things aren't in a nice straight line? Well, first of all, we represent vectors with arrows, little drawings. We're going to be dulping an awful lot. One way to add them, Rob, would be to very carefully draw them to scale. So let's suppose in example 4, it says we want to add 5 kilometers west and 8 kilometers north. You could say, oh, I'll draw a line 5 centimeters long, west, pointing left. I'll draw a line 8 centimeters long, pointing up. And then you could carefully measure the distance between them and use a protractor. Forget it. We could. So we could draw a scale diagram using a protractor, or better yet, we could get tricky with it. And here is the rule, and it is in bold font. To add 2 vectors together, we draw them tip to tail. How do we draw them, Dane? How do we draw them, McKinley? Hey, Halen, let's suppose I wanted to add 2 vectors together. How would you suggest that I draw them? Tip to tail. Tip to tail. Emma, I've got a hankering to add 2 vectors together. Any suggestions on how I might want to draw them? Tip to tail, you say? Okay. How do we add 2 vectors together? We draw them tip to tail. What that means is the arrow point of the first vector touches the tail point, starting point of the second vector. Oh, and then the resultant is from the tail of the first to the tip of the second. So example 4 asked, John travels 5 kilometers west and 8 kilometers north. What's his resulting displacement? Let's use trig. Let's try example 4 right here. I have learned anytime they give me directions, Emma, it's worth drawing the little compass rose. Darian, what was the first vector they gave me? It said John travels what? Magnitude and direction. And then plus, what direction does he travel? Now, I've drawn them roughly to scale. I know 8's not quite twice as big as 5, so I've drawn a vector not quite twice as big as 5. Jeff, how do I add 2 vectors together? How would you suggest that I draw them? Yeah. So here's the answer. I'm going to go 5. There's the tip. The tail of the next one goes right there. 8. The resultant is going to be, now here's what I wrote, from the tail of the first to the tip of the second, but I hope even from your diagram you can see, oh, it's going to be pointing upwards and leftwards. Yeah. Here is the resultant. I'll call it vector R. How could I find the magnitude of the resultant? Kai. You're saying 8 squared plus 5 squared equals R squared. How big is R? Calculator, please. This won't work out evenly. Do you get 9.43? 9.4? Kilometers at, that's the magnitude, but I also need a direction. How do I get the direction? The direction is where the vector is coming from. Look up, look up, look up, look up. It's going to be that angle right there. How do I find that angle? Let's get tricky with it. See that angle that I want, Dane? See it sitting there? Okay, looking at that angle, that 8, opposite, adjacent, or hypotenuse? Sorry? Opposite? What about that 5? You know what? A good habit would be to write the word Sohcahtoa at the top of your page. Because I've got an O and an A. Hey, which trig function am I looking for? Sorry? I didn't hear. Tangent. Tangent. What always goes next to the trig function? The angle. Do I know the angle? Yeah, it's a variable. Equals opposite over adjacent. How big is angle theta? You need to know how to do this on your calculators. So can all of you try to find theta? I wasn't here for your lesson, so I need to make sure you're all in degrees. Dost thou haveth a calculator? Yes, thou dost. See if you can get that, 58 degrees. Anybody not able to get that 58 degrees? Now is the time to ask, and I'll come show you happily. Yep. What did you get for your angle theta? 58 degrees. So I would say the direction is 58 degrees. What of what? Look up, look up, look up, look up, look up. To draw this, I always go to the horizontal or vertical line. Never start on the angle. What's the horizontal or vertical line? This one. What direction is that? It's going to be north of west. Go up from west, except up is north. What of what? North of west. Or you could also go with 32 degrees west of north. 32 degrees west of north would be if you found that angle, which gets you to the same spot. You would get that is, the way you would get that one would be if instead of going 5 plus 8, you went 8 plus 5. You end up with the same vector. For each of these, for all these, I take 2 answers. All of us will have the same magnitudes. Some of us will have the 90 minus that. It's called the complement angle, and those will be different. We'll talk about that in a second. Let's try example 5. Let's suppose I want to add 10 newtons east and 6 newtons south. Find the resultant. FR for resultant. Dulp. First, I've scrolled down, so I'm going to add a compass rose. First thing I'm going to do then, 10 newtons due east would look like this. Plus 6 newtons due south. You know what? 6 is about, Trev, half of that 10, but a little bit more than half. So I'll draw a line pointing south down, a little more than twice as big as that 10. I want to be roughly to scale. In other words, I would not draw 6 like that. That'd be silly, because now I'm going to get weird answers that just look scary. You'd get the right answer still, but it wouldn't look like your triangle, and you'd freak out. So 6 is about there, give or take. Trevor, I'd like to add those 2 vectors together. Any suggestions on how I might draw them? Yeah. So you're saying I go 10 and 6, and the resultant is from tail of the first to tip of the second. There is the resultant. Let's get the magnitude. Well, 10 squared plus 6 squared equals f squared. 10 squared plus 6 squared square root. Whoop. Do you get 11.7? Units, 11.7 what? There's the magnitude. That gets you 1 mark out of 2. Direction. And again, Trish, to find the direction, we go back to where the vector started, top left corner. And we say, oh, that's the angle that I want. By the way, drawing that, before I find how big theta is, can you tell me what the what of what is going to be? North of south, east of west, what of what? Let's see. To draw that, what direction did I start out going? And I went what? This is south of east, not east of south, south of east. So I'll leave a little space here. I'll go at south of east. Now let's find out how big theta is. Gesundheit. Atla, my friend, since you want some attention, that's 6, opposite, adjacent, or hypotenuse. I agree with you. How about that 10? Which trig function do you think you'd like to use? Tangent. And it's going to be the tangent of the mystery angle equals opposite over adjacent. All of you, please try this on your calculators. Even those of you who borrowed one from me, please try this. Get theta. 38 degrees, I think, but don't quote me. 39? 31? Oh, yeah, you know what? That was dumb math. That was terrible math. 30.1? Let me go see. Shift 10, bracket, 6 over 10, close bracket. How about 31 degrees, right? Not 30.1, 31 degrees. Okay. This is how, Trish, you do math with directions. You add them. How? Draw them. How? Draw them. Tip to tail. Jake, you know how I draw them? Tip to tail. Do you know what I mean by that, right? Tip to tail. Here's the nice thing. It doesn't matter which order you draw them in. Put your pencils down, look up. I could have drawn the 6 first and then the 10. I would get this. 6, 10. Fourths. When I do Pythagoras, I'll get 6 squared plus 10 squared square root. Is that the same magnitude as we had before? So that doesn't change. Oh, I'll find this angle here, because that's where I'm coming from. That's where my resultant is starting out at. Face down on the right block, please. Thank you. That 6, opposite, adjacent, or hypotenuse. Adjacent. That 10, opposite. Which trig function? Still tangent again. It's going to be shift tan of 10 over 6 as opposed to 6 over 10. And I get 59 degrees at 59 degrees. What of what? Start out here, go that way. East of south. Is that dark enough? You guys can't see that at all. My old projector, that was a nice dark yellow. East of south. What did we get in our version? More specific. You know what? We found that angle. 31 degrees south of east is 59 degrees east of south. Doesn't matter which one you pick, what order you add them in. In other words, McKinley, what's 6 plus 3? What's 3 plus 6? Just like in arithmetic, the order you add numbers doesn't matter. In vector math, the order you add them doesn't matter. McKinley, what's 6 take away 3? What's 3 take away 6? Oh, does the order matter in subtraction? You get a different answer. We'll learn later on how to subtract vectors. There, Anthony, you have to be a lot more careful. A plane is flying due north at 132 meters per second. A crosswind is blowing due east at 44 meters per second. What's the plane's resultant velocity relative to the ground? So here's where some of this is used. In particular, it's used a great deal in airplane flying where there's a crosswind. Now, I've made up the numbers really nice. Our crosswind is exactly blowing towards the east. In real life, it's never blowing exactly. It's blowing at angles, but we're starting out with nice 90-degree angles in our magic physics world. So we want to add V plane plus V wind. That's going to give us V ground. Let's add vectors to all of that. The velocity of the plane added vectorially with the velocity of the wind will give me the resultant velocity that the radar tower sees, the ground sees. Anthony, what's the plane's velocity? Direction. You know what? Valoria, what's the wind's velocity? East 44. 44, is that more than half as big as 132 or less than half as big as 132? About a third, roughly, is. You know what? I'll draw it about a third as long. Plus, and east is to the right. Yeah. We want to add those together. In fact, I should probably make that a little longer even. Any suggestions on how I could add two vectors together? Draw them tip to tail, you say? Really? I never thought of that. So you're saying I can go 132, 44, and that's my VG, velocity relative to the ground, my ground speed. It's, by the way, they call it ground speed. They should call it ground velocity, but those that are in aviation, I believe they still call it ground speed, not ground velocity. So I'll use the terminology, even though the physics of it is like fingernails on the blackboard. It's not a speed, it's a vector. And calm down, Mr. Duke. Calm down. Let's find the ground speed. Any suggestions? Which trig function could I use to find the magnitude? Pythagoras, you say, really? Now, if you reach the point where you can do Pythagoras all on your calculator in one step, I'm okay with that. In other words, if you go 132 squared plus 42 squared equals square root, I'm okay. I'm going to write in my notes what we're doing. 132 squared plus 44 squared equals VG squared. $139.1, but we'll go to 3 sig figs. So the ground speed magnitude is going to be 139 meters per second. Direction. And this is certainly what you're more interested in. If you're ever wondering, this is, for example, airline pilots, this is what they do to make an estimate if they know their headwind or their crosswind, how long it's going to take for them to land, to arrive at their destination. They're doing this very quickly, finding their ground speed and dividing it by their distance. Now it's all done with software. Used to be done by hand. Where my vector starts, Jake, down here, there's theta. By the way, theta is going to be what of what? East of south, north of west, what of what? Start out going north, and then east of north. Yeah? Yeah. I'll leave a little space. East of north. Now let's find theta. Hey, that 44, opposite, adjacent, or hypotenuse? I think opposite. How about that 132? Which trig function? Mr. Dueck, I figured it out. It's always tangent, isn't it? No, but the vast majority of the time, yeah, I'll come up with a couple of weird ones where it's not tangent, but usually you'll know the up-down vector and the left-right vector, and you'll be finding the slanty vector, usually. There will be a couple of questions where I give you the slanty vector, give you one of the up-down vectors, and say find the other one, and that's where it won't be tangent. But here, tangent of, mystery angle theta equals opposite over adjacent, shift tan, opposite over adjacent. Y'all get 18.4 degrees? So 18.4 degrees east of north, or if I felt like going north of east, how many degrees would it be? Go 90 minus 18.4. Sorry? 72? Good gosh. Don't tell me my new pen has started to act up the way my old one did. Maybe not. Or 72 degrees. Is it 72 or 71.6? Yeah, whatever. Okay. So we can add velocities tip to tail and find the resultant. We can add forces tip to tail and find the resultant. We can add momentum tip to tail and find the resultant. We can add accelerations tip to tail and find the resultant. We can add displacements tip to tail and find the resultant. We can add, I think that's it for you guys this year for vectors. There are more out there, but that's it for you. Number 1. Homework. Try number 1. Now this is in a nice straight line. You have gravity pulling down and air friction up. This is a winner minus loser. Wow, my little pen's acting up. I just told them yesterday that my pen was fine. Oh, you know what? I think my whole computer's acting up. Let's go like this. Let's see, am I back? Now I'm back. Okay. Number 2. This, no, I did that trying to recover my pen, so we're back. Number 2, this will be find the magnitude and direction, magnitude and direction of what would exactly cancel out the first 2 ants. Number 3. Number 4. And I didn't include the answers. Okay. Now, number 4, there's 3 vectors. Little advice, add that and that first, and then add that to the east.